In this video, we're looking into different kinds of compounds that we often encountered in inorganic chemistry. This would be a factual kind of video where we'll be understanding different facts related to the color of compounds so that it becomes comfortable for us to predict the color of compound whenever they are asked in any questions. And also we'll understand the relationship between the polarizing power or polarizability and the intensity of color of different compounds. So first of all, we must remember this particular order of polarizing power of these few cations. These are the cations that we'll often encounter in most of the questions related to inorganic chemistry. So we see the trend here that polarizing power is decreasing from left to right. If you look at the color of the compounds that are formed using these cations, then we encounter similar trend here too, because to the left we have black brown color of Bi3, and then red color of HgI2, and then yellow color of AgI, finally white color of CdI2. That means intensity of color is decreasing from left to right. So from these two facts we can conclude that polarization or polarizing power or even polarizability and intensity of color are directly related. Next, we can also see here that Cl and Br and I, we have different kind of anions, but the cation are same, that is Az. So as we go from left to right, the size of the anion is increasing, and so polarizability is increasing, and so intensity of color is also increasing from white to pale yellow to yellow. Now for Be2 plus and Al3 plus, we know that the size of Be2 plus is less than Al3 plus. So BeF2 is covalent in nature because polarizing power of Be2 plus is much greater than Al3 plus, and AlF3 is ionic in nature. Now we also must remember the order of this polarizability of these many anions, because this will help us to predict the intensity of color. Greater the polarizability, greater the intensity of color. Now some facts here, as was told, we must remember it, that is all phosphides are black in color. Phosphides means formed using this anion. Most of the sulfides are black in color, means formed using this anion. You can see the polarizability is very greater for P3 minus and S2 minus. So it is told that most of the phosphides and sulfides are black in color. Now exception is there. Exception is in the case of CDS, where the color is yellow, in MNS where color is light pink, in ZNS where the color is white, and for HGS where the color is vermilion. And all the D block oxide plus lead oxide except ZNO are colored. ZNO is a white colored oxide, that this we must remember. All chloride and fluoride are white colored, because we know that fluoride and chloride are having smaller sizes relatively, so their polarizability is less, and so they are white color. That means the intensity is not too much of these colors. Now Ag plus and Hg bromides are colored, and Ag plus Bi plus 3 Hg and Pb plus 2 iodides are colored. These are the facts that you can remember, you must remember actually, because lots of questions are asked related to color, so it's not too much to remember. You can just keep revising these facts so that it's always in your mind whenever you are solving questions related to color of compounds, and it will be very easy for you then to predict the color of different kind of compounds. Now we have this flowchart here. We have Pb, we'll start with Pb and we will add oxygen and heat it. We'll get PbO. If you continue heating it without the addition of oxygen, it will get converted into PbO but with a different structure. Here the PbO would be at less temperature, it would be tetragonal in structure, but at higher temperature it would be orthorhombic in structure. When it would be tetragonal in structure, it is called litharge and its color is red. When it is in orthorhombic structure at a higher temperature, it is called massicot and its color is yellow. Now if we heat it and supply oxygen to it, we will get Pb3O4, and we can see that oxidation number is subsequently increasing. Here its oxidation number was 0, here is plus 2, here is plus 8 by 3, here it will be plus 3, and here it will be plus 4. Now we can remember the color here, red, orange, and then here brown black, and here black. You can see as the oxidation number is increasing, so its intensity is also increasing, because cation is becoming more polarizing. Cation is able to polarize the anion by a larger degree, as the oxidation number is increasing. This was a factual based thing. You must remember it. Questions may be asked from these parts too. Now we have this ordering of covalent character. If you can remember the polarizing power of the order that was told here, like if you remember this, then you can conveniently order the covalent character, because polarizing power and covalent character would be directly related. So these points you can infer from the order of polarizing power. Now we have this fact that Sn2 plus acts as reducing agent. Obviously we have learned that Sn wants to be in +4 oxidation state. So if it is in +2 oxidation state, it would desire to be in +4 oxidation state, and in the process of getting oxidized to a +4 oxidation state, it would reduce the compounds in the reaction. That means it would act as a reducing agent. Now to prevent the oxidation of tin, what we do, we keep a piece of tin in glass bottle, so that when it would oxidize to Sn4 plus, it again gets reduced to Sn2 plus. Now we have Sn2 plus here and Sn4 plus here. That means we are adding this particular agent so that Sn2 plus is getting oxidized to Sn4 plus, and in the process this particular agent is getting reduced to this particular agent. Now here we see, if you see here, what is the oxidation state of Mn? We find that oxidation state of Mn here is +7, and on reacting with Sn plus 2, Sn itself gets oxidized to +4 and reduced Mn plus 7 to Mn plus 2. Similarly, for you can find here for Cr, what's the oxidation state? Oxidation state is 7 into 2, it's 14 minus 2 divided by 2. Basically it's +6, and on reacting with Sn plus 2 reduce it to +3 state, and Fe3 plus is reduced to Fe2 plus state, and Au3 plus, Hg2 plus, Bi plus 3 is reduced to Hg, Bi and Au state, and the color of all these ions are given here. So this was a factual kind of video on the color of compounds. Basically there is no shortcut to remember the color of a particular compound, but it's not that difficult. You can keep on revising the color of different kind of compounds, and by the time you will be sitting in your exam, you can comfortably remember the color of various kind of compounds, because from now on you will be practicing it in several different topics, such as now we'll do heating effect, will form their different kinds of compounds. Then after the formation of compounds, you can recall what should be the color of compound. Again, in the further topics such as salt analysis, will again dealing with several kind of compounds. At that particular time also you can keep on recalling the different kinds of the different colors of different kinds of compounds. In that way, by being in consistent practice, consistent remembrance, you can actually remember the color of different kinds of compounds by the time you sit in your main examination. In next video, we'll be dealing with another important and exciting topic, that is heating effect, where we'll be heating different kinds of compounds and see what would be the products that would be formed in the heating of a particular kind of compound, and also we'll try to keep on recalling the color of various kind of compounds that would be formed as a product, so that we will be able to remember the color of different kinds of compounds by the time we get prepared for the examination.